Hey, how's it going? Come on in. It's about to get going here. All right. Do you have any questions over 12.5 or anything else? Everyone's so quiet. Everyone's so shy in here. No issues? We're ready? All right, well, we are going to cover a lot of material today in terms of sections, because these sections are pretty short. There's not a lot to them. Like 12.6 is 2 pages long, 12.7 is 2 pages long. So we might even probably get into 12.8 today. And we'll be into chapter 13 next week, which will be nice. So right now in two-dimensional space, we had two coordinate systems that we like to use. We had the Cartesian coordinate system, and we had polar, right? And in three-dimensional space, we have Cartesian, which is x, y, z, and then we have other coordinate systems that we can use. And so the second one that we have is called cylindrical coordinates. So you'll remember, hopefully from polar, that, let me see if I can get this. Yeah, here we go. Cylindrical coordinates is basically a three-dimensional version of polar coordinates. That's all it is. You remember in polar coordinates, what we did is we converted our x-coordinate to r cosine theta, the y-coordinate to r sine theta. Remember that? And this is what it looked like. If somebody gives you a radius, right? Somebody gives you an angle, then in two-dimensional space, this point corresponds to an x value and a y value, but in Cartesian, there's an x and a y, but in polar, it's a theta and an r. Well, now what we're going to do is we're going to extend this to the 3D system. We use the same conversions for the x and y coordinate. We still have the same Pythagorean identity, x squared plus y squared is r squared, but now we need to handle the z coordinate. What do we do with the up and down? And in cylindrical coordinates, you don't do anything with the z coordinate. You don't convert it. It's just z is just whatever z is. So z stays as itself. And then there was another relationship we had that if we knew what the y and the x value were, we could always recover the angle. And that we did in polar also. So let me show you why they call this cylindrical coordinates. A cylinder looks like a beer can, right? So here's our two-dimensional space. If now I pop this out of 2D, so here I popped it out of 2D now, and I'm in three-dimensional space, I'm going to rotate this around. You can see that, spin this. Here we go. So our x-axis is coming out this way. Our y-axis coming out this way. I can change my radius, right? Change my radius. I can change my angle, which would spin me around, right? And then the z-coordinate is just going to stay z, so it just can go up or down. So imagine taking this point where it is, fixing the radius, taking it, spinning it around. I would draw a circle, right? But now move the z-coordinate up and down, and that's going to create a line, wouldn't it? And so imagine spinning that line around, and you would get the cylinder, wouldn't you? And so everything in this coordinate system looks like a cylinder, so we call it cylindrical coordinates. Does that kind of make sense? Whenever we're in cylindrical coordinates, notice that when we look at it from the top, our regions are polar regions on the ground, which means that we can handle some regions that we could not do prior to this. Like normal triple integrals that we were doing before, when we looked at the shadow on the ground, we were hoping they were type 1 or type 2. But what if the shadow on the ground is more polar? Well, we would convert to cylindrical coordinates and then handle it that way. Does anybody remember, though, with double integrals, what you had to do if you converted from Cartesian to polar in a double integral? What you always had to include in the integrand? The r. That r. Remember that r always popped into the integrand? So don't forget the r. Same thing's going to happen here, because really what we're doing is we're leaving the z variable alone, which means with the triple integral, we're leaving the inner integral alone. The middle and the outer integrals that used to be with respect to y and x are now going polar, so they're going to be with respect to r and theta. And so because they're going to polar, the r will now appear in the integrand again. But we will address that when we get there. First, let's look at a general picture of a three-dimensional solid here. Okay, so I'm looking at a region E, okay, three-dimensional region whose shadow in the xy plane is a polar region. So we have this three-dimensional solid, right? On the ground, notice that the region down here is a polar region. It is your angle, right? Your angle is stuck between two constants, alpha and beta. Your radii are stuck between two functions of theta. Now, usually for us, these radii are fixed. But remember the problem where you had to drill out the hole? That circle was not fixed radii. Your r was a function of theta. So this is a more general picture. By the way, I have not even started grading those because they are on my to-do list. They're the next thing up, so hopefully I'll have those done soon. So if we have this scenario where your theta is between two constants, your radii are stuck between two functions of theta, and then your surface, right? Your surface, or your solid above it, is bounded between two surfaces. Those two surfaces are still u1xy, u2xy. However, because we have converted from Cartesian to polar, we can't use u of x1y, or u1xy. We have to convert those x and y's to polar also. But that's a general picture. Questions on the general picture? All right, so here's the way we deal with the triple integral in cylindrical coordinates. Given a region E, if your theta is between two constants, your radius is between two functions of theta, and now look at your z coordinate, right? Your up and down is stuck between u1 of xy, but see I've converted xy to r cosine theta, r sine theta. u2 of xy is now u2 of r cosine theta, r sine theta. Then your triple integral over E is going to be this. Now remember, E is just your domain, right? It's your region of integration. We're integrating a function that's in four-dimensional space that we can't see. But that region is a cylindrical region. So we're integrating this function of x, y, and z with respect to V, respect to the infinitesimal volume. Triple integral, the outer integral, alpha to beta, is with respect to theta, right? Because that's a restriction on theta. Our h1 theta, h2 theta is our restriction on the radius, so our inner integral is with respect to r. And then this integral, the inner integral, is between the two surfaces, and so that will be with respect to z, because we have not changed z in the problem, because in cylindrical you leave z, right? Yes? All right, so what we'll do is our function that we're integrating, it was f of x, y, z, is now Replace the x with r cosine theta, replace the y with r sine theta, and leave the z. Don't forget the r in the integrand. I didn't point that out, but here it is. There's the r that comes from the conversion to polar. Now, I'm saying conversion to polar. Everyone understand we're actually converting to cylindrical, but I always say polar. I don't know, I've always said it my whole life whenever I'm doing this, because you really are converting this part of the triple integral to polar. All right, so here's our first example. Oh, I didn't bring my lecture notes today. Oops, okay. Well, I want to do the triple integral over the region E of x dv if E is the region bounded by z equals 0, z equals x plus y plus 5, the cylinder x squared plus y squared equals 4, the cylinder x squared plus y squared equals 9. Triple integral over E of x dv. The region bounded by z is 0. Z is x plus y plus 5. The cylinder x squared plus y squared was 4, and then x squared plus y squared was 9. That's our region. This right here is our definition of E. So we need to get some sort of visual idea of what that region looks like. So z equals 0 is what? XY plane, the ground, right? Z equals x plus y plus 5 is what geometrically? A plane, right? And that plane, let's see, at x is 0 and y is 0, z is 5. So if I'm looking above the origin, it's up there somewhere and it's got some tilt to it, whatever, but I have a plane. So I've got the ground, I've got a plane. So that looks like that's going to be the lower surface and upper surface, right? And then I have these cylinders. These cylinders are running parallel to which axis? The z-axis, so they're vertical, I guess you could say. The first one has a radius of 2. Second one has a radius of 3. So it's the region bounded by all of those. Do you see it or not? Yeah, okay. Yeah. You could say it's like a washer on the ground, so it's hollowed out in the center. And then imagine moving it up and then cutting it with the plane. So, I don't know. Maybe something like this. The ground, the plane, an outer cylinder, an inner cylinder, and it's the region bounded by all of those. Somewhere in here, something like this. Do y'all see it? Yeah? The computer's slow today. Is that what you were thinking? Something like that? Okay, so this is our E. This is our solid region of integration. So we need to define that region of integration. From last class, we would look at the shadow on the ground, and if we look at this shadow, it's not really a good type 1 or a good type 2. The shadow of this on the ground is your washer, right? So let me try and draw this thing out. I was asked by one of your classmates the other day, like, should you try and draw the 3D picture or the 2D picture first? And I think it always just depends on the problem and how difficult it would be to draw the 3D. If the 3D is, you know, just some planes and like tetrahedron stuff, you might be able to connect lines and make things look good. This may be a little more difficult to do. with the plane and then the cylinders, might get tough. So I'm going to start with the region on the ground. I know that the one cylinder comes in, has a radius of 2, the other one has a radius of 3. So I have an inner circle. Not the best circles I've ever drawn. And so the shadow on the ground is all of this, right? So do you agree at this point that this is really suited for polar coordinates? Yeah? Because if I look at this, I can say that that region is defined by all points, all polar points, where theta is between where and where? Theta is between 0 and 2 pi. And then what can you tell me about the radius of every point there? It's between 2 and 3. Yeah? So for the triple integral, like we did in the triple integrals last class, in last class you needed to find restrictions on x, y, and z. Here we're going to need to find restrictions on theta, r, and z still, because we're not switching z. So I still need my restrictions on z. So this is where your kind of understanding of this and what all of these were, without me showing you the picture, comes into play. I mean, you really have to kind of see it without having to draw it, because without a drawing, you know, what are you going to do, right? So we can tell here that the ground is what? Z is going to be 0. So I know that z is going to be between 0 and what? X plus y plus 5. However, I'm not allowed to use x and y, because I've converted to polar, haven't I? So everywhere that you see x's, they have to be replaced with r cosine theta, and everywhere you see y's, they have to be replaced with r sine thetas. So this restriction actually changes from this to r cosine theta plus r sine theta plus 5. So that's your x plus y plus 5. Agreed? Yeah? Once you have your 3 pieces, theta, r, z, restricted, you can set your triple integral up. So I'm going to set it up now. My outer integral is going to be my restriction on theta. So 0 to 2 pi. My inner integral, or middle, sorry, integral is going to be my restriction on r, which was 2 to 3. My inner integral will be my restriction on z, which is 0 to r cosine theta plus r sine theta plus 5. What am I integrating? What's the integrand? They wanted x, right? Can I just plug x in? No, I have to replace x with r cosine theta. Right? That's the x that I'm integrating right here. Now I need to write the dv. The dv is going to be my 3 things, right? My 3 integral differentials. We said dz doesn't change, but then dr d theta. But because I went to cylindrical coordinates, or because I went to polar, I always have to remember to include that r, right? That r has to be in there. And at this point, we can integrate. So on my first inner integral, right, I'm going to integrate this whole thing with respect to what? Z, which z isn't even there, so I treat all of this like a constant. So the antiderivative of this can be pretty clean. I think I will work through this one. Whoa. Unless I get to a point where I don't want to work through it anymore. So it's integral 0, let's see, r cosine theta plus r sine theta plus 5 of r squared cosine theta dz. All right, this is my inner integral, which should be the antiderivative of r squared cosine theta is, with respect to z, is r squared cosine theta times z, evaluated from z equals 0 to z equals r cosine theta plus r sine theta plus 5. When I plug 0 in, it's going to go away, so I'm pretty happy about that. Now I've got to plug in this for z. I'm not very happy about that. So we have r squared cosine theta times r cosine theta plus r sine theta plus 5, and that's it, right? I subtract, I plugged in 0, it's gone, so I don't need that. And now I'm going to distribute through here. This is r cubed cosine squared theta plus r cubed cosine theta sine theta, and then plus 5r squared cosine theta. So there's my antiderivative with respect to z evaluated at those two endpoints. And that's what goes into my middle integral. So now we do the middle. The middle integral is the integral from, thank goodness, two constants, 2 to 3, right? I'd really suck if they were functions of theta, because that could become a big mess. I'm integrating all of that, right? I get to cheat. With respect to r, which isn't so bad, right? Because, I mean, this is 3 terms, and the r is times the cosine squared theta, so that's all a constant. So it's just power rule on these r's. So I have 1/4 r to the 4th cosine squared theta, plus again 1/4 r to the 4th cosine theta sine theta, and then plus, what, 5/3 r cubed cosine theta, evaluating from what r though, right? R equals 2 to r equals 3. Ugh. All right, so let's plug in 3. What's 3 to the 4th power? 81. 81/4. So I'm getting 81/4 cosine squared theta, plus again 81/4 cosine theta sine theta, plus r cubed is 27, but then divide that by 3 and you get 9, and then multiply times 5 and you get 45 cosine theta. I take all of that and I subtract from that what I get when I plug in 2. 2 to the 4th power is 16, right? Yes? 2 to the 4th is 16. Divide by 4. So 4 cosine squared theta. And then again 2 in here, you get 4, so plus 4 cosine theta sine theta. Almost done. What's this? 2 cubed is 8. times 5, 45 over 3. 45 thirds? Yeah. Did I do that right earlier? 9, oh, I did 9 times 5. Yeah, 40 thirds. Earlier, it was 9 times 5. I forgot what 8 times 5 was, okay? Sorry. And then cosine theta. Ugh. I have like terms here, don't I? Cosine squared theta, 81/4 cosine squared theta minus 4 cosine squared theta. Is it 4 on top? So 16, 81 minus 16, 45, right? 65, 85, 105. Who cares, right? It's a number. And then we have same thing here. But then you're adding here, right? And then over here to here, right? What's that? Oh, yeah, subtracting. Minus, right? Distribute through. So, okay, let's write it down. What do we have? Combine these together. 65 fourths, or 65 fourths. Do y'all agree? Cosine squared theta. 65 fourths again. Cosine theta, sine theta. And then plus, what do we have here? What is it? 95 thirds. I have to really think about that stuff. My brain doesn't work that way. Like my brain stopped wanting to do arithmetic a long time ago. It just said, forget it. I guess it's one of those things where it's like, I know I can if I need to, but I don't. It's like I'm reserving that space in my brain for other things. Okay, are we all right with this? This is going to be our inner integral. Let me check something. I think I have it worked out here. Yeah. Okay. This was my Mathematica doing it. The difference here is that Mathematica used some trig stuff to convert things over, and so we can't follow that. Let's just see if we get to 65 pi over 4 at the end. All right. So now this is our inner integral. This is going to go into our inner integral, or outer integral. This is probably the only problem I'm going to work fully through today. So now we are in the outer. So it's this integral from where to where? 0 to pi. D theta. So how are you going to integrate this first one here? Probably do like a power reduce on that first, right? Make that 1/2 plus 1/2 cosine 2 theta. Remember that formula? Okay. So maybe I'll rewrite that first. 0 to pi. Let me go 65 over 4 out here. This becomes 1/2 plus 1/2 cosine 2 theta d theta plus 65 over 4 integral, I'm going to rewrite it this way, sine theta cosine theta d theta. On this one, it's just a basic substitution. U is sine theta. I forgot my theta in there. Right there. U is sine theta, derivative is cosine theta, d theta. So that'll work pretty clean. And then this one, well, do we need to talk about that? 95 thirds integral cosine theta, d theta. All right, here's the antiderivative. I have 65 fourths, 1/2 what? What's the antiderivative of 1/2? With respect to theta? 1/2 theta, right? And then the antiderivative of cosine 2 theta is 1/2 sine 2 theta, but then there's a 1/2 out here already, so it becomes 1/4 sine 2 theta. Is that all right? Now, all of these, right, all of these are the same limits of integration, so I'm just going to write all the antiderivatives out, and then at the very end, I put 0 to 2 pi. Plus the next one, 65 over 4. What is the antiderivative of sine theta cosine theta d theta? One half sine squared theta. Right, derivative of this, the 2 would come out, hit that, and then you would have sine theta, and then derivative of sine theta is cosine theta, so that's this. And then the last one, antiderivative of cosine theta is sine theta. And now we have from 0 to 2 pi. Okay. Here we go. Yes. What? Is what all 0? Okay, yeah. Everywhere we have sine, when we plug in 2 pi, what do we get? 0 on all of them, except for that right there, right? So it's just going to be, what, 2 pi plugged in there is just pi. So we get 65 pi over 4, right? That's what we get when we plug in 2 pi. Then we plug in 0, right? We plug in 0, and then everything is 0, right? That's 0, sine of all those things, 0, 0, 0, sine of 0, 0. So we get 0. So we get 65 pi over 4. Is that what Mathematica told us? Whew. Good. Feel better about that. So I'd say, let's see, that problem took us maybe like 15, 20 minutes. But the calculus 3 part of it took us how long? 5? Right? I mean, you could argue that the triple integral is a calculus 3 idea, but each one of them individually is just a cal 2 thing. There's really not a whole lot new there. So it's all about the setup is the most important thing. Now this really opens up the types of integrals you can do, triple integrals, the types of regions you can handle, because now your shadows can be polar. Find the volume of the solid between the cylinders x squared plus y squared equals 4, x squared plus y squared equals 16, which also lies within the sphere x squared plus y squared plus z squared equals 36. So you have a cylinder that opens up parallel to the z-axis, has a radius of 2. Outside of that, you have another cylinder parallel to the z-axis, opens up, has a radius of 4, right? You're looking for the volume between those two, which is, again, your washer that's going infinitely up and down. Now, you come in and say, but it's got to be within the sphere. So you come in with the sphere and you close it off. And in there is your solid. So you want to know the volume of that. Are we all aware that we are not talking about this part of the sphere? It's only between the cylinders and inside the sphere. So you try and visualize it. Is that what you were visualizing? Is that what you kind of saw? It's almost like a cylinder, like a solid slug, right? That has a hole drilled out of the center, except that the tops are not cut straight off, right? The tops are actually curved with the sphere. Yes? And the bottom is curved. And you've got hollowed out, of course, in the middle. So, what do you think? We saw last time that when it comes to finding volumes of solids, one of the applications of triple integrals was that if you did the triple integral of 1, right, on the region E, that gives you the volume of E. So all I need to do is come up with some sort of representation of the solid E and then integrate the constant 1 function, triple integrate the constant 1 function, and that'll give me the volume of that red thing. So let's talk about this red thing. What is the shadow of it on the ground? And this is where things get a little weird, because you actually don't have a shadow on the ground because this thing actually goes through the ground, right? But you could still talk about its kind of projection onto the ground. What is that thing when it cuts through the ground? What does that look like? It looks like that washer again, doesn't it? Which is a great polar region. So I think we're going to be able to handle that region pretty easily. Inner circle, outer circle, polar, it will be nice. The cap on top and bottom is the part we have to think about here, right? In the last problem, it was z equals 0, and the top was that plane. Here, the bottom is what? It's not a surface. I mean, it's a surface, but it's not a plane. It's what? It's part of the sphere, right? And the top is another part of the sphere. So maybe we can do it this way. Does everyone agree that that thing is symmetrical? Meaning that I could just cut it in half, find that volume and double it. So let's, instead of going to the bottom of this thing and the top of this thing, let's just cut it right in the middle, which means the lower limit of integration for z would be what? 0, right? Then the top is still part of the sphere, but we'll handle that in a second, all right? Let's try this. So we had volume of the region bounded by x squared plus y squared equals 4, x squared plus y squared equals 16, but within the sphere, x squared plus y squared plus z squared equals, what was it? 36. What's the radius of the sphere? 6. All right. So I'll start with the ground image. I need some work on my circles. So with that region, which is, like we said, perfectly suited for polar, what are my restrictions on theta and r? 0 to 2 pi, right? And then my radius restrictions, 2 and 4. And now I need to come up with z. And we said, again, we're going to cut it in half, so we're going to use the ground as 0. And then I need the top of this. Now we said the top was the sphere, right? Which means that you need to go take that sphere equation and solve for z, right? Solve for z. So let me take this thing and solve for z. If I did, I would get z squared 36 minus x squared minus y squared, which means z is equal to the square root, plus or minus, right? The square root. And we are only going to look at the plus because we're looking at the top. So had we not gone to 0, right, then we would have the plus root over here and the negative root over here. We're going to go from 0 to the plus root and double the answer. It's only because it's symmetric, right? That's an important little subtlety here. It's because it's symmetric that we can do that, and it's because we're trying to find its volume. If we were integrating a function, and this was our solid, and that function that we were integrating was something we didn't know too much about, we could not cut this in half. All right? We couldn't. So this is going to become 36 minus r squared. What? What happened? What happened? Yeah, we can't have x and y's in our thing, right? And it just so happened that it really works out great, doesn't it? This 36 minus, I factor the negative out, that's x squared plus y squared. But we know that because in polar coordinates, the relationship between r, theta, x, and y, we know that x squared plus y squared equals r squared. So I can swap out x squared plus y squared with r squared here. I actually could have done it right here, too. I could have just said, hey, look, that's r squared. Now move it to the other side and do the same thing, and you would have got this. So that's it. I think we're ready to set it up. I have a triple integral. I'm going to double it, right? This will be equal to the volume of what I'm looking for. I'm going to double the triple integral. It goes from 0 to 2 pi. It goes from 2 to 4. It goes from 0 to root 36 minus r squared. What am I integrating? 1 times r, good, thank you. Then d dz d r d theta. We're integrating the one function because that's what you integrate when you want to find volume. You have to include the r because you went from Cartesian, three-dimensional Cartesian, to cylindrical or polar. And then dz, because it's a triple integral, you have all three variables are present. And in cylindrical coordinates, z is z. So that still has to be there. So your first antiderivative is going to be the antiderivative of this with respect to z, which would be what? rz. You plug in this for z, you plug in this for z. When you plug in this for z, you would get r times this. And then you plug in 0 for z, it's gone. And then integrating r times this would actually be nice because that would be a basic substitution. I'm not going to go through this one because that was too tedious, the last one. Now, when I decided to do this, I guess last time I did this, I went ahead and did the top and bottom surfaces. I didn't double the answer. And it probably worked out a little worse. But at the end of it all, okay, when you get through all of this, here's that first integration right here, antiderivative. And then you keep going, blah, 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 and then you get approximately, this answer is the exact answer, and this is your approximate answer, 383.595. See if that's the right page. It's not. Let me make sure these problems 7 through 19, 17. Oh, wait, hold on. I was looking in the wrong section here. Triple integrals, cylindrical coordinates. That's correct as far as the numbers, but it's off of page 734. It's only 3 problems. So please keep in mind that in this section, your conversion because we're in three-dimensional space, we're saying our shadow down on the ground is a polar region, right? The shadow of E on the ground is polar. But just like last class, you could project a shadow onto a different plane other than the ground. So you could have a polar region on the side wall here or this side wall here, which would change a lot of things. You would still do a polar conversion, but instead of doing well, no, that's not it. Instead of doing x equals r cosine theta, let me draw this over here so you can see what I'm talking about. This is x and y and then z. If your polar region was like a disk on the ground this way, and then let's say over here, you cut this, we'll go back to something like that. So there's your solid. Do y'all kind of see that? So when you take this solid, E, and you project the shadow over onto the xz plane, your xz plane shadow is polar. You could still do this, but instead of making these substitutions, x is r cosine theta, y is r sine theta, and z is z, you would do what? What here, the cylinder is going this way, right? So your y doesn't change. Your y is the top cap and bottom cap. So you would leave y as y. You would let x be r cosine theta, and you would let z be what? R sine theta. And then everything works the same way. I'm not going to ask you that, but I just want you to see that this can all be extended onto other planes, but then your variable changes too. Make sense? We just don't attack that sort of thing here. I guess most people would say that's a natural extension of what we've done. So it would be expected that you understand it, but not necessarily something I would ask you to do. Okay, so let's go back before I introduce the next section. Let's go back to the whole idea of Cartesian and cylindrical. So if I'm standing at the origin and I want to get to the projector, Cartesian says I'm going to have to know what x is, right, a certain distance. I'm going to have to know what y is. Come right through here. I'm off. Okay, so I'm going to that little thing instead. And then I need to know what z is to get up there, right? X, y, z, I can be up there. That's Cartesian. Cylindrical says what? Get me to that. Okay? The angle, so I start by pointing out the x-axis, right? And I say, give me an angle. Then, give me a radius, right? And then, give me z, and I'm there, right? That's cylindrical. Either way, you can get to that point in three-dimensional space using both of those coordinate systems. There's a third that we use. Spherical coordinates. So let me explain it by walking around the room first, and then I'll put this all up here. Man, this is the only room that doesn't have like a big long yardstick, and it's the one room I wish I had one. You don't see one in here? I know, I've used markers, they always start falling apart everywhere. Oh well. What's that? What do you have? Yeah, an umbrella, that'll work. It's a cute umbrella. Okay. So, I want to get to that thing again, right? Here's the way spherical works. And it's kind of odd, but you don't start pointing out the x-axis. You actually start pointing, just looking straight up like that. And then the first thing I give you, okay, is a theta to turn, okay? Then I give you a phi, which is an angle that's measured from the z-axis down to where I'm pointing to the fire thing up there, right? And then I give you a radius, but we don't call it r because we don't want to confuse it with the Cartesian. We call it rho, the Greek r. And so if you give me a rotation theta and then an angle down from the z-axis phi, and then a rho, I go out to that same point, don't I? And that's spherical coordinates. Now I'll show you why it's called spherical with the animation, but remember that with cylindrical, if I were to go out there with cylindrical, right, I would rotate, walk out, and then go up. And we said that if you start swinging that thing around, a line, you start drawing cylinders. Okay, what do you think you're going to draw if you start swinging things around here with spherical? Spheres. So here. There it is. Okay, can you see it? You have the x-axis, you have the y-axis, you have the z-axis. So you start out, I'm actually going to give you a phi first because you're not going to be able to see anything unless I give you phi. So I give you a phi, and that tells you how far to rotate down from the z-axis. So there's your phi. Now, can y'all see we're kind of still in the xz plane here? I haven't rotated. But see where my point is right there? And now I turn my theta, and I start swinging through. Man, it comes out so much better on my thing. But you see I've rotated into like the first octant here. And then, of course, your rho is controlled. That's how far out you want to go. So if I can control theta by swinging around, I can control phi. Then imagine leaving your rho, your radius alone, and just letting phi and theta vary. Then it's like someone standing here like swinging a ball around the room, right, with the fixed radius, and it draws a sphere. Yes? See what this does. Oh, that's zoomed into the first octant. What else do I want to say about this? Okay, there are some restrictions here. We have to be careful with spherical coordinates because if I don't need the umbrella, but if I'm over here, right, and I want to get to that point over there, the fire extinguisher, then I rotate by theta. I phi down to it, right? But what would happen if my theta can go all the way around, right? My theta can spin all the way around here and my phi's point out. Then couldn't I point this way and let my phi swing all the way backwards like this? See what I'm saying? And I could get there also. So we put a restriction on the phi so that it never swings back around. And so our phi is always going to be between 0 and straight down, which would be pi. Does that make sense? That way you're never actually going around to the other side into these other octants. Same thing with the radius. Yeah, the rho is always going to be positive or 0. So there it is. All right. We have with spherical coordinates, first let's talk about the restrictions. Theta has to be between 0 and pi, so this rotation is between 0 and pi, 2 pi, right? Your phi only from 0 straight up, pi straight down. Your rho has to be a positive number or 0. And then remember with polar coordinates we had, or cylindrical, we had conversions. X was r cosine theta, y was r sine theta, z stayed z. Not in spherical. The spherical conversions are pretty messy. You convert x there we go. X does not become r cosine theta with spherical. X becomes rho cosine theta sine phi. I want to make sure cosine theta sine, yeah, I follow the book. I want to make sure I follow exactly the variables that they use. Okay? And then your y becomes rho sine theta sine phi. And then your z becomes rho cosine phi. That's every time you go to spherical coordinates, those are the conversions you have to make. And then you have this, it's kind of like the Pythagorean identity, but it's your spherical identity. X squared plus y squared plus z squared equals rho squared, which you could actually verify if you wanted to. If you square that, square that, square that, add them together, you should get rho squared. Now, I'm not going to get into why we do these conversions, but it can all be done pretty easily just using these triangles in here and looking at the relationships. You know, the x coordinate, right, is for that point up there is an x coordinate. And if I draw that x coordinate down here, then I can create a right triangle and I can get relationships between theta and phi, and I can go through all that geometry and I can come up with this relationship. But it's beyond what we're going to do here. If you want to do it as an exercise, it's pretty, I don't want to say fun, but it's pretty interesting to go through it. All right. Any questions on this? Okay, so in cylindrical coordinates, in cylindrical, what we just did, when we had our theta between two constants, and our radius between two constants, and our z between two constants, our region looked like this. Right? Theta was between two constants. The radius was between two constants. Our z here is between two functions, right? And that's what it looked like. So if I look at it, you know, from the top like this, that's what the shadow on the ground looked like, and that was like a polar region. My question to you right now is, if I tell you in spherical coordinates that your phi's between two constants, your theta's between two constants, and your rho's between two constants, what does it look like? Can you visualize that? Like a dome, yeah? So let's just say, let's say I'm pointing out at that fire extinguisher thing. Let's say that's some theta, that's some phi, that's a fixed rho, right? Now imagine that I change my theta a little bit. So I swing my theta between two constants, right? I get, do you see what it is? Almost like a little arc of a circle up there. And then let's say I change my phi back and forth a little bit. Now I have another circle, but it's going this way, right? And so imagine I do that and I do that all at the same time. So it would shade in this like surface, right? That would look like part of a dome. And then imagine allowing my rho to go back and forth between two constants as you're doing that. Would it look something like this? You see that? It's like a section of this thing. I hope that visual helps you see it. It's not squared out though, right? This thing tapers in to the origin. So if you look at it from the outside, you know, from this side, from the outside, these are arcs of a circle. This is an arc of a circle. This is an arc of a circle. That's an arc of a circle. As you go in, it tapers in towards the origin. So that's a very strange looking box, right? That's what a region E would look like in spherical coordinates. What you lose here is there's no more idea of a shadow on the ground. We have no shadow on the ground with the spherical region. With cylindrical, we looked at the shadow on the ground. We said, oh, that's type 1, type 2, that's polar. Here, because of the way it's defined, you can't do that. So let's see how we're going to handle a triple integral and spherical. And let's see the way a problem would be presented. Oh, forgot something. If your theta is between two constants, phi is between two constants, rho is between two constants, your triple integral sets up this way. So you have, of course, alpha to beta, c to d, and a to b. And then your function is a function of x, y, z. So you have to replace x with your conversion to spherical, your y with your conversion to spherical, your z with your conversion to spherical, and then you will integrate with respect to rho, phi, and theta. But what the hell is that? What the hell is this? Well, you know how we said that in converting to polar coordinates that r always popped out? And I tried to show you, if you go back and look at it, I tried to convince you where the r came from. I showed you geometrically. I think some of you got it. You may have forgotten it now, but I think I convinced a lot of you where the r came from. With spherical, I'm not going to be able to convince you geometrically at all. But in spherical, this is what pops up. It's not just rho, it's rho squared sine phi. And that has to be included every single time you convert from Cartesian to spherical coordinates. The next section that we're going to do after this one is a formula on how to get this if you do any conversion from any coordinate system to any other coordinate system. But for now, we're just going to take it on faith that that's what it is. So do not forget the rho squared sine phi in the integrand. Find the triple integral over E, right, of e to the square root of x squared plus y squared plus z squared with respect to volume, where E is the region in the first octant between the spheres of radius 4 and 9. The region between them. Let's talk a little bit about why we wouldn't want to do this with the Cartesian and why we wouldn't want to do it with polar. And so I'm focusing right now just on E, all right? Just on the E. Why is it that, what does that look like? The region in the first octant. So this classroom is the first octant, right? It's been the first octant the whole time we've been here, right? So the region that is in the first octant, but between two spheres. So imagine a sphere coming through this room, right? It would go through that wall. It would come through like a circle, wouldn't it? And it would have a radius of what? 4? And then there would be another circle that would come through this room, and it would be, what, radius 9, yes? Then on this wall, it would be the same thing, right? Radius 4, radius 9. And then on the floor, it would be what? Radius 4, radius 9. But it's the stuff between the spheres, right? So if I were walking in here, I would come to a radius of 4, and I would have this shell right here, wouldn't I? It would be curved like this. Do you all see this or not? And so it would be curved, and then I'd kind of break through that, and then I would be inside the solid, and then it would be another shell on the outside. I'm just trying to get you to visualize it before I actually just show it to you, because this is no fun if I just show it to you, right? I mean, there it is. What's that number down there? Why did I put that number down there? I don't know. I'm going to get it out of there. I don't like it. Hold on. There. All right, much better. All right. Is that what you saw? First octant, region between these two spheres. Why would I not want to do this in Cartesian or polar? Why could I not do it in Cartesian or polar? Look at this thing from straight up and down. Well, if I can get it to be straight up and down. That's about as good as I'm going to get, straight up and down. Say again? They don't meet? How do you mean? Yep, you have a top and a bottom. I think I have a top and a bottom here, don't I? I have the top, this is the top sphere, and then the bottom is this. But wait a minute, hold on. It's only this, right, in this little region. Like, the top is that one, right? And then the bottom one is this one just in here. But when I get outside here, it's actually, the bottom is the ground, right? And the top is the sphere. I don't know if that's what you were saying. You could cut it into two polar regions, but your two integrals would be different. So, again, let me try and come up here. What's that? You could, this would be this on the ground. Okay, so let me go back before I address that. Does everyone see that this is the top, this is the outer sphere, right? And so that outer sphere, the one with the radius 9, is the one that's always on top, yes? If we're looking at this from the sense of Cartesian or polar. The problem is that the bottom one is different. From here to here, inside this region here, it's actually the bottom is the other sphere right here. And then over in this region, the bottom is the ground. So we would have to split it into two different regions, and then you'd have to decide, am I going to do it Cartesian or polar? Let's look at this first one. I've never liked this one little part of Mathematica. It's always hard to get that little circle so I can rotate it. All right, so let's say I want to go type 1 region. And I have to focus just on this piece. I can't even think about this yet. If I look at this as type 1 region, I'm going to have an upper function and a bottom function, right? The upper function will be part of a circle. The bottom function will be a line. So I could do that Cartesian. I mean, I could, right? But then I would have a separate integral that would be this region. Do you see that? And how are you going to do that one? You would have to cut it here, and then you'd have to say between here and here, it's what? This is the top circle, and this is the bottom circle, and then over here it'd be this is the top, and then the bottom is the ground. It's just going to become a disaster. You could probably do it, but it would just be more work. What we should instead convince ourselves of is that this is just a very, very basic spherical region. It's a spherical rectangle. Exactly. It's a spherical rectangle. Well, it would be a spherical cube if they were all the same distances, but I guess you could. Yeah. Spherical parallelepiped. Yeah, it's better terminology. But yes, the same idea. We had the idea of a rectangle in polar coordinates. This is the idea of parallelepiped in three three-dimensional space. Good, very good. And actually, what is a parallelepiped in cylindrical coordinates? Wouldn't that be hollowed out in the middle? Because what, your radius is stuck between two constants? Your theta, well, it doesn't even have to go all the way around. You could have like a slice of this. Like take this section out. I don't know if that makes sense, but your z's between two constants, your theta's between two constants, and that'd be hollow, wouldn't it? Your theta is between two constants, and then your radius is between two constants. Yeah, on the bottom. We've got to cut that out. Hold on. Right there. What do they call those? I've seen those before somewhere. Where have I seen that? Yeah, it's the letter C just drawn backwards. Yeah, stretched through space. Yeah, yeah, that's exactly what it would look like. All right, this is good. I like this. This is interesting because yes, this is what it looks like when you hold the three constants in spherical coordinates, the three variables in spherical coordinates between constants. We've got our thetas fixed, right? Looks like our thetas between what? We're in the first octant, so 0 to pi over 2. Now our phi always starts from the top, right? So our phi is going from where to where? 0 to pi over 2 again, right? And then our radius, how far you're allowed to go back and forth, is stuck between 4 and 9. Well, that's about as clean as it could possibly get for us. So you see, you compare that to trying to get it into Cartesian or polar. I mean, it's just, we're going to have all sorts of crazy different scenarios. No. I mean, if you can understand what this thing looks like, you don't really need drawings. You go straight to your theta, your phi, and your rho. Theta, we said, was between 0 and pi over 2. Your phi was also 0 to pi over 2. And your rho was 4 to 9. And that means my triple integral is going to set up super nice. Because they're all constant, does the order matter? Because they're all constants. No. Does not matter. Now, what does matter is the function we're integrating. And we were integrating, what, e to the square root of x squared plus y squared plus z squared? And that was a very carefully chosen function to integrate because even, let's say even if you got it into Cartesian, right? Even if you had done that, that's going to be a disaster to integrate. In fact, probably impossible to integrate without going to some sort of power series or something on it. You'd really have nothing that you'd be able to throw at it. So even a clever application of different sectors of Cartesian or polar, we'd still be stuck here. But because this is spherical now, we remember that kind of the like Pythagorean identity for spherical, similar to it, says x squared plus y squared plus z squared is rho squared. So this is the square root of rho squared, which is means this is just e to the rho, right? E to the rho. Assuming rho is positive, the square root of rho squared is just rho. And then, because we went to spherical, what always pops into spherical? Rho squared sine phi, right? And then you're ready for your differential. D rho d phi d theta. Have y'all heard phi or phi? Phi? I know, I always hear phi. People always want to correct me and say phi. I've always said phi. I've heard both. I think if we all understand each other, I think it's okay, right? Like if we understand what we're talking about. Same thing, have y'all heard of Euler, the mathematician Euler? Euler? Okay. People call him Euler, people call him Euler. So I'm not here to argue. As long as we understand, we can communicate what we're trying to say. It's all that makes sense. That's all that matters to me. Tomato, tomato. Potato, potato. Does anyone say tomato? Who says tomato? Anyone say tomato? You say tomato? Okay. So that one, if you do say tomato, you're wrong. All right? No. All right, so how would you integrate this? You have to go with respect to rho first. So you have to integrate e to the rho squared. By parts, twice, right? You would have to do by parts twice to get that one to work through. Yes, you could, but what would happen was if you did, like, let's say theta first, then it would be all of this with a theta. Then you would tack in two constants, which would still give you just numbers in front of all this. Eventually, you would still have to address e to the rho squared. Nice try. I mean, I would have thought the same thing too. Like, let's try a different order and maybe it'll work. But do you see what I'm saying? Like, when you throw theta in here first, the antiderivative of all of this with respect to theta is all of this theta. Then plug in your two constants. You're still going to have all of this times a constant. So it stays there. It stays intact through the other integrations. You could get all those done first if you wanted to. Yeah. Yes? I'm not sure I'm following you. Are you agreeing that we could do that? It doesn't hurt? Get what out of the way? I want to make sure we're clear that you cannot avoid the integration by parts. Okay, okay. I thought you were saying something else. Okay. We won't be able to avoid it. We'll have to do it at some point. But you are free to change the integration order as long as you change this order also. So I'm not going to do this one. It would be integration by parts twice. But here it is worked out. When I did this on accident, I typed it in 2-3, but then in mathematics I did it correct 4-9. And so you go through all this, blah, 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 and you get 826,482. I don't know what this is. And I think this was me doing it piece by piece, but It's the end of the notes. I mean, really, spherical coordinates is just about getting you to see regions that could be very complicated in a different perspective, and then perhaps make the integration at least doable. So spherical coordinates came number 22 and 23. You know what? Make that 22, 23, and 24. I think 24 is interesting. But this is page 740. Minutes. What are we supposed to have gotten through today? Because if we are caught up on our syllabus, I'll cut you loose early today, but if we're not, November 5th, Is today the 5th? Shit, man. We're supposed to start and get into 13.1 today. All right, so we have 20 minutes. Hang in there. Let's get through 12.8. Let's try and at least address 12.8. Okay, so when I first made the notes for 12.8, the first time I ever did, I was very ambitious. I was like, I'm going to try, if I can, to explain geometrically where this thing comes from that we show you in this section. And over the semesters, I've tried to explain it. And the problem that I run into every time I run through this explanation is this one part of this explanation. Where is it? Right here. Because I have to, at some point in trying to explain what's going on, I say I'm waving my hands at this, basically saying it's difficult to understand this. And I don't like ever having to do that. And the reason why it's difficult is because we have not talked about a vector function of two variables, have we? We've done r of t or something like that. We have not done r of uv. And so we don't know what this looks like. And it's later in chapter 13 that you actually get introduced to this. So to prove to you now why this works is kind of like putting the carriage in front of the horse. You know, you have to understand this before you can understand the reasoning behind it. Turns out that this right here, do you remember what r of t graphed, a vector function of one variable, what it graphed? Or a curve, right? R of t. Now, that was our first vector equation of a line, was r of t equals r naught plus tv. But then we said that if you don't make it a certain way, and you let each of the vector components be just some functions, whatever they are, you could draw these cool curves. We drew spirals. Remember that stuff? But they were curves in three-dimensional space. If we throw a second variable into it, what we can draw in three-dimensional space are surfaces, which is really, really cool. Because now I'm not talking about a surface where you have a sheet and on the bottom you have domain. I'm talking about a surface that the variables are like independent variables like time in the background, and you can draw sheets that turn on themselves and cut through themselves, and you no longer have this domain restriction that you had before. Again, I don't want to get too far ahead. So every time I try and go through this damn proof, I always run into an issue in this, and I lose students. And so when I continue through, they're pretty much gone at this point. And then I just get to the point where they're like, okay, and here's the formula. They're like, okay, is that the formula? And I'm like, yes, and that's all they want. So I'm going to do the same thing here. I'm not going to run through this because it could take us 45 minutes for me to try and convince you of this formula. All right? Let me just get to the final thing here. All right. So here's the concept here of a change of variables. Now, I'm going to show you what's called a change of variables with a double integral. This can be extended into triple integrals, quadruple integrals. We will just look at double. If you have a double integral, right, so our region D is in what space? Our region D is in two-dimensional space, right? That's a two-dimensional domain, right? A triple integral, our region is three-dimensional, solid. So we have a double integral, so our region's on the ground, of f of xy with respect to area. So there's our double integral. This formula says if you want to come in here and change your x's and y's to something else, like when we converted to polar, we said x was what? R cosine theta. We said y was r sine theta. That was a change of variables. We changed x to something new. We changed y to something new. If you want to do that, you are free to do that however you want to. It's fine. Go ahead. Do it. And it doesn't have to be r cosine theta. I could just come in there and say, look, everywhere I see an x, I want to make it r plus 2 theta. I could just make that up. Just pull it out of the air. That's the way I want to change my variables. And then make my y something completely different. I'm free to do that. However, Your integral is going to change in this way. Your function, you have to replace the x with what you said it is now, and usually it'll be a function of two things. With polar, it was r and theta, wasn't it? Here we're just going to use something more arbitrary, u and v. So just imagine that's r and that's theta. So your x now becomes that new transformation, that change of variable. Your y becomes new, and then you're now integrating with respect to u and v separately, right? Two variables, u and v instead. So that in polar was what? Our r and our theta? But then there's this thing in here. When we convert it to polar, what always popped in there? The r, right? Well, that r actually comes from this formula. It is what we call the Jacobian Determinant. And it's this computation we do where we take our equation for x. Remember, x is going to be transformed into something. We take the partial of that x with respect to u times the partial of the y transformation with respect to v. We subtract the partial with respect to v of x, and then partial partial of y with respect to u. We compute this. We take the magnitude. Whatever the hell that is, it has to go here. With polar coordinates, it's r. With spherical, it's what? Rho squared sine phi. Okay? But see, the spherical is a triple integral. So that Jacobian determinant changes if you're in a triple integral because it's more complicated. The Jacobian determinant is more complicated in three-dimensional space than it is in two. So where does this word Jacobian determinant come from? I will go back in my notes here for this. No, maybe not. Do y'all know what a determinant of a matrix is? If I have a matrix of 2 by 2 matrix, have y'all seen a matrices before? Like, let me give you an example: 4, 3, 2, negative 2. Right? If that's a matrix, and I ask you for the determinant of this matrix is A times D minus B times C. Have y'all seen that before? Okay. If you haven't, it's not going to be the end of the world because you have a formula, you just go off of that. But the determinant is when you do this times this. And so if you go back and take a look at this right here, okay, right, I guess I can just give it to you in this formula. This is like your A and then your D minus your B and then times your C. So let me go back to my picture. It's kind of like AD is this part right here, and then minus the BC, which is this part right here. So you could actually create a matrix made out of this in the top left corner, and this in the top right corner, and then this in the bottom right, and this in the bottom left. Does that kind of make sense? And it's a determinant. I'm just trying to give you where the name comes from. Determinant is from the idea of the matrix, and then Jacobian is because Jacobi, the mathematician, was part of the invention of this whole thing and the logic behind it. Now, there are some restrictions. I mean, you can't just do an arbitrary change of variable out of the blue, like, and it's guaranteed going to work. Like, there are some restrictions on what that transformation can be. And if you look at the book, that's the wrong page. No, actually, that is the right page. On the top of page 746, don't open your book or anything. It actually goes into the actual change of variables and double integrals, like conditions you have to have. Like, there are some things that have to be different. Like, can't just come in with some discontinuous functions that aren't well behaved on the region, you know, that become asymptotic and things like that. You can't just throw any transformation in there. But if your transformations are nice, this will work. Now, there's something else in here that's very subtle I haven't talked about. Does anyone else see it? Something else that changed in there? What's that? Yes, this S. The S. That's going to be the hardest part for us, really, is because what happens is if here everything is in terms of x and y, you're looking at an xy plane. When you transform that region over, in polar coordinates, we know what the rectangle went to, right? A rectangle in Cartesian went over to a polar rectangle, and we know what that looks like. But if you do some transformation that's not polar transformation, then that region, that rectangular region in Cartesian, is going to map to something new. And whatever that is your new region. And you need to know what it looks like, because you need to be able to determine if it's type 1, type 2, or even polar, if you're going to be able to handle it. All right? So let me start this whole thing off. Now that I've given you the formula, let's take a look at a specific transformation. Let's see if we can come up with all this. All right? I'm going to take, right now, I'm going to try and do a double integral of f of xy dA over some region D. But what I'd like to do is I'd like to make a conversion now, a change of variables. I'd like everywhere that you see an x, I'd like for you to replace it with u cosine v. Everywhere you see a y, I'd like you to replace it with a u sine v. Now, what am I really doing? I'm just trying to trick you, or not trick you, I'm trying to hide it behind u and v here. What am I really doing? That's a polar conversion, isn't it? That's polar conversion? I'm just replacing r with u and theta with v. So I'm going to come in here and I'm going to say change this way. Change it. So according to the formula here, my new integral is going to be what? F of x of uv, y of uv. So this new integral becomes double integral f of x of uv. See, x is a function of u and v. So that'll go here, u cosine v, comma, u sine v. That's my function of y, right? Y is a function of u and v. So that's just like me putting r cosine theta, r sine theta. Then I need to come up with the Jacobian determinant, right? That's the next piece, the Jacobian determinant. So I need to find the partial of x with the, let me write it on the board because we're going to need it a few times in here. Oh man, I'm almost out of time. It's the partial of x with respect to u times partial of y with respect to v minus partial x with respect to v times partial y with respect to u, right? Come here. Move it down here so I can work with it. So now the Jacobian determinant here. Maybe some partials here. What's the partial of x with respect to u, which is the first thing I have over here? What's the partial of x with respect to u? So you're treating u like your variable and cosine v like your constant. So what's the derivative of this? Cosine v. Okay, what is the partial, the next part of the Jacobian determinant, partial y with respect to v? What's partial y with respect to v? U cosine v. Good. Now, I'm supposed to multiply those two together, right? Multiply those two together, and that'll be the first part of the Jacobian determinant. So multiply those two together, and what would you have? U cosine squared v. Okay. Now, I also need for the Jacobian determinant partial of x with respect to v. What's that? Negative u sine v. And then the partial of y with respect to u, which would be sine v. And then I'm supposed to multiply those two together, and put them here and subtract them. So I'd have minus, and then it came out to be negative u sine squared v. Yeah? And then at the end, I have du dv, right? Du dv. What does this turn out to be? U, right? You factor a u out of those, you get sine squared v plus cosine squared v is 1. So you get u. And wasn't u the radius? Wasn't that really r? So do you see how Jacobian determinant here, the change of variables, this formula does look like it works? Yes? I'm still not trying to convince you of why. I'm just, you see it worked once, hopefully it'll keep working. All right? But this is the way we, now, what we still would have to determine is what happened to our region. So check this out. This is going to be, like I said, the hardest part of everything. I mean, taking partial derivatives, that's not going to be tough. But let's just say we had a rectangular region. Let's just say it looked like this. This was our D. We would have never wanted to convert to polar if that was D, right? We would have just kept it in Cartesian. But let's just see what happens to something like that. I'm just going to make up some values here. Let's say that's A. Let's say that's B. Let's say that's C. Let's say that's D. The question is, what happens when you do your change of variables through here? What does this look like in my new polar region, where this is U and this is V? And that's going to be the hardest part of it. So I'm out of time. I don't have time to treat this, but let's just leave that as like, that's where we'll pick up, is with this. I'll leave you with one more thing. The reason why we'd want to do this, okay? Why would we want to do this? Well, if we have a region that looks like this in Cartesian, right? We know that when we take that over to polar, right? This right here should be easier to deal with as a polar region, shouldn't it? So what we're going to see is that we take a region that's complicated, or maybe even not a circle. Let's just say it looks like, would you ever want to integrate this region? Would you ever want to integrate that region there? As type 1, type 2, it would just be a pain in the ass, right? So maybe there's a change of variables that when we map this over, maybe it turns it into a rectangle. And then it's a very easy integration over here. That's our goal, is to take a complicated region, change the variables so that when it maps over, it's something nice. All right, I think we're good, right? I know I've got like another take-home quiz that I got to get you. I'll start looking at that. I might email it out or something. But you've got homework to do too, so get caught up. Have a good weekend.